a recording to Facebook. So like, I don't understand. Okay. So quantum numbers are the very, very basics that get us to being able to write an orbital diagram. And then we can also translate that orbital diagram into electron configurations. Okay. But as we learned, I don't know, Friday, I think it was, we can also go from the periodic table straight to the electron configuration. So we don't have to start at the really basic stuff, the quantum numbers. We can actually start from the periodic table to get these electron configurations, and then actually we could work backwards to all of the other stuff. So that's what the double arrows I'm trying to represent. Like, these things are all interconnected. Obviously, when we learned them, we had to start by learning about the quantum numbers, or else it wouldn't have made sense what we were talking about when we're like 1s, 2p, all of that. But we don't necessarily have to use that just to list an electron configuration, okay? So I'm going to do quite a few examples where we kind of like show the different ways you can tie all these together, and then we'll try to use those same elements, and we'll talk about the size and ionization energy that we were hitting at the end of class last time, okay? So if I look at the periodic table and I look at sulfur, I do not have to do anything other than just look at its position on the periodic table, and I can very quickly identify its valence shell and even the electron configuration of that valence shell, okay? So it's in the third row, and it's in the P block, and it's 1, 2, 3, 4 elements into the P block. So I can immediately say the valence shell is going to have 3p4 as its outermost subshell. Okay, remember subshell is the N and the L together. So like 3p would be the subshell. We're not talking about the individual orbitals. We're talking about that set of orbitals. In the main group elements, this is a key point I feel like I didn't emphasize enough in the last classes. In elements that are in the main group elements, the d orbitals are not considered part of the subshells. Sorry, part of the valence electrons. So even in something like selenium, which is one step further, the electron configuration, the abbreviated of selenium would be argon 4s2 3d10 4p4. Okay, we would not consider the d's to be part of the valence electrons. This is true of any main group element. It's just the S and the P. So if you're asked about valence electrons, you say there's 6 of them for selenium. And what are those 6? The 4s2 and the 3p or the 4p4. Okay? The reason is because once you fill the d orbitals, they stop reacting at all. They are not going, those d orbital electrons are not going to react. Even I don't really have a clear explanation or like understanding of why that works, because if you're in the d orbitals, like if we're talking about, let's just use something like early on, titanium, okay? So titanium would be argon 4s2 3d2. Those would be considered, all of those would be considered valence electrons, okay? So titanium would also, or sorry, not also, but would have 4 valence electrons. You would include the S and the D because it's not in a main group element. It still has unfilled D subshells. In selenium, that D subshell is completely filled in, so we do not count it as part of the valence shell because it will not react. In titanium, that is the electrons that are reacting. We do consider them part of the valence electrons. So if you're talking about a transition metal, you include the S and the D. If you're talking about a main group element, you just talk about the S and the P. Okay? Okay, so when we are now looking at sulfur, see, this is what I mean by like, I'm just kind of like throwing stuff at you that I think is important information. So when we're looking at sulfur, we said based on its location on the periodic table, we know what the valence electrons are, the outermost ones at least. And for a main group element, it has to be the S and the P. In addition to 3p4, it would also be 3s2, okay? So without doing any kind of complicated work, just by looking at the fact that sulfur's in the third row in the P block, 4 elements in, we now easily predicted what the valence electrons are, like where they are. Or if we tacked on the neon, now we actually have the abbreviated electron configuration. Okay, if we wanted the full electron configuration, we would need to do that like row by row thing where we say 1s2, 2s2, 2p6, and then the rest of the valence electrons. So we could do that as well. 1s2, 2s2, 2p6, 3s2, 3p6. 3p4. So we can easily get electron configurations from the periodic table rather than working from the quantum numbers and the orbital diagrams. Also, we could go backwards from the electron configurations back to the orbital diagram, right? Because the electron configuration is just telling you the subshell and how many electrons there are. And also it does it in energy order, so you can draw the orbital diagram accordingly. So like, let's do that for sulfur. 1s2, okay, 1s orbital, 2 electrons. 2s2, 2s orbital, 2 electrons. 2p6, 1, 2, 3. 1, 2, 3, 4, 5, 6. Okay, did you have to know additional information there? Yeah, you had to know that if there's 6 electrons, there must be 3 in that p subshell because you can only hold 2 electrons per orbital, right? But like, I'm pretty sure that like everybody in all of my classes knows at this point that there's 3p orbitals, right? Like, I don't think anybody is forgetting that. Just in case though, don't forget every orbital can hold 2. So if there's 6 in there, there must be 3 orbitals. Okay, next 3s2. Guess I should label that. So 2 in the 3s, and then 3p4. Now the only mistake you might make here, so this is what sulfur should look like. The only mistake you might make there is like not remembering that you have to separate out the electrons, like you can't pair them up. You have to separate them out until it's necessary to pair them up. So like this would be the correct orbital diagram for sulfur. This would not be correct. Okay, it has the right number of electrons, but they're not in the right place. This is like applying Hund's rule when we put it in this way, okay? The other thing we call this, we say it's the ground state orbital diagram. It just means it's the one we've done that's lowest in energy. We've only looked at orbital diagrams, electron configurations for lowest energy configurations. So that's called the ground state. That's why I haven't like specified that word a lot, because we haven't done anything other than ground state. All right, any questions that have popped into your mind as we're talking? Okay. I think I want to do like a basic overview of quantum numbers. So this is chapter 8 stuff at this point, and then we'll take some of these elements and talk about size and ionization energy with them. Okay. All right, so this is chapter 9. I'm heading back to chapter 8 now. So when we talk about the quantum numbers, let's just do like a quick recap on the 3 first ones and kind of like what values they can have, what it means, and then how that translates into the orbital diagrams and the electron configurations. Okay, so now we're kind of like taking this thing, instead of starting from the periodic table and working, we're going to start from the end and work forward, just to show you like they're all connected and there's just different ways to get to the right answer. Okay, the reason I'm not talking about M sub S is because it only has those two values, plus 1/2 or minus 1/2, and you know that the two electrons in an orbital have to have different m sub s values, okay? That's a relatively simple quantum number to handle. The other ones are the ones that define the orbitals, so each set that involves these three will define a given orbital. So like when we look at the orbital diagram, for the 1s, there is a particular n, l, and m sub l value that define that orbital. Okay, so n is not contingent on anything else. N can be anything starting at 1, any integer. We call it the shell typically, or the energy level, or the principal energy level. All of those terms are interchangeable. And what does it mean? It just means the distance away from the nucleus, okay? You can think about this almost equivalent to the Bohr model, where we have like the little picture with, the circle around it, and we say n equals 1, n equals 2, n equals 3. That's pretty much what it is, okay? And like I've said probably 1,000 times at this point, the closer you are to the nucleus, the lower in potential energy. So that means n equals 1 is lower in potential energy than n equals 3. Okay, so when we look at the orbital diagrams, and I'm even going to go down to, where did that one go? I swear I had, I think I meant to make these notes closer to that nice big, this one. That's unfortunate. Okay, if you scroll down in your notes, there's this nice pretty orbital diagram, blank orbital diagram, that has all the quantum numbers incorporated. So usually when we draw the orbital diagrams, we write the subshell designation, so like 2s or 2p, but we don't remind ourselves that s, p, d, and f correspond to a numeric L value. So don't forget s, p, d, and f are representative of an L value of 0, 1, 2, and 3. So if I'm talking about like the 2p subshell, I don't have to just say 2p. I can say n equals 2, L equals 1. Okay? So this orbital diagram is nice because it reminds you of that. So like all of the s's, they're trying to give you the L value up here. So like on your notes, write L equals, and then that's this value. So all of the s orbitals, they have an L of 1. All of the p orbitals have an L, I just said 1, L of 0. All of the p orbitals have an L of 1, d, 2, etc. And then, just in case I forget to come back to this, the m sub L values are what's listed underneath the orbital. So this is like way more complete than the orbital diagrams we usually draw, but that's what this stems out of. This stems out of the quantum numbers. Okay, I don't want to go back to that other page that I had because it's way too far away. So I'm going to talk about L here, and then maybe we'll go back to it. Okay, so we said n can be 1, 2, 3, etc. It's not dependent on anything else. L is dependent on n, okay? So when we talk about allowed values, we mean L can't just be whatever it wants to be. It depends on which shell you're in, okay? So L is going to be some value 0 through n minus 1. When we first did this, I think people are like, I don't know what that means. What we're saying is that there are limited L values given the n you're in. So in n equals 1, the only L value we have is 0. Okay? 0. S. In n equals 2, we now have the L values of 0 and 1. In n equals 3, we now have the L value of 0, 1, and 2. And then in 4, we have 0, 1, 2, 3. If we went up to 5, we would have 0, 1, 2, 3, and 4. Okay? So that's what we mean by 0 through n minus 1. You're always going to go up to everything one number below whatever n value. So if we're at n equals 16, we're going to have 0 through 15. Obviously, we haven't talked about letter designations for anything beyond L equals 3. We certainly haven't talked about any shapes beyond that. So that's the other thing about L, is don't forget that the physical meaning is it determines the shape of the orbital. So if I give you a picture of an orbital, you should be able to identify, is that S, P, D, or F? And also you should be able to tie that back to the L value. So like I could say, indicate the L value associated with this orbital image, right? And if it's like, you know, the one with 2 lobes, you'd be like, oh, that's L equals 1, or a p orbital. Okay? The D's generally look like 4 orbitals or 4 lobes. They also have that one that's like 2 with the ring around it, and then the F's are much more complicated. So they've got like 8 lobes or 2 with 2 rings. Just like familiarize yourself with the images. You're not drawing them, obviously, because this is a multiple choice test. Okay, so allowed values starts at 0, everything up through n minus 1, which means every time we increase in n, we get an additional shape of orbital. And the physical meaning is the shape. Don't forget too, shape has an effect on energy. Because if you're spherical, you can get closer to the nucleus than if you're shaped like this. And then the d orbitals are even more restricted, okay? So the shape has an impact on the energy as well. Which is why when we show S, P, and D, like if we look at n equals 3, why they're staggered in energy, because the shape is inhibiting those electrons from getting closer to the nucleus. Okay, now I will go back up here. Right, okay. So then M sub L, also dependent on the previous quantum number of L. So M sub L is a range of negative L through positive L. We don't actually care about the actual values because they don't have an effect on energy, okay? An M sub L of negative 1, 0, and positive 1, they're all the same energy. What we care about is how many values there are. So I just said everybody knows now that p orbitals, there's 3 of them. That's because L equals 1. So M sub L could be negative 1, 0, or positive 1. There's 3 values, which equates to the fact that there's 3 orbitals. So the types of questions that you see that are in chapter 8 are much more theoretical than the ones in 9 are like a practical application to elements. So by that, I mean, you might get questions in chapter 8 that are not things that you would actually see with real elements. So for example, I've seen lots of the practice questions that are like, here's a list of quantum numbers, which one is not allowed? Okay, so something that would be not allowed would be like n equals 4, L equals 4, right? Because L has to be 1 less than the n value. So you cannot have an n and an L equivalent in a given orbital. Or maybe n equals 4, L equals 3, M sub L equals negative 4. That is also not allowed because the M sub L is limited to negative L to positive L. So if it's 3, it has to be negative 3, negative 2, negative 1, 0, 1, 2, 3. Okay, so those are the kind of like more theoretical type of questions you'll see that are more typical of chapter 8. Another one somebody asked me about that was like a good reminder of the types of things you would see is she's like, it asked about how many M sub L values L equals 16 has. And I'm like, yeah, we've never talked about an L equals 16, right? Because no element, no known element, at least not in its ground state, is going to have an L of 16. Okay? However, we can theoretically predict what the M sub L values would be. It'd be negative 16 through positive 16. Okay? How many values is that? Well, it's 16 on the negative side and 16 on the positive side and a 0 in the middle. So if you know the L, you know that M sub L, there's going to be 33 values. You could list them all out, but like, you know, try to, you know, take a shortcut a little bit if you can. There's like equations, right? Like the M sub L is 2L plus 1, right? So 16 times 2 plus 1 is 33. Don't try to memorize those. Just try to like think through logically what would make sense. Because I guarantee you'll like forget. You'll be like, was it L plus 2 or is it 2L plus 1 or is it 2L minus 2? You know, you'll forget. All right, last like theoretical type question. I don't know, something like more complicated, like maybe it would say how many electrons can be held in a set of orbitals where L equals 5. Okay, so if L equals 5 and you want to know how many electrons could be there, you're going to have to think about how many orbitals are there, and then each orbital can hold 2. So an L of 5 should have 11 M sub L values, right? -5 through -1, 0, and then 1 through 5. And each of those can hold 2, so that would be 22 electrons. Okay, so this is all theoretical. Then it ultimately leads to these orbital diagrams, because we're basically synthesizing all the potential values within a given shell to get that nice, pretty picture. So that's how we would get from quantum numbers to the orbital diagrams. Okay? So this is my point. You can go from both directions. Now I'm going to take a breath for a second and let you guys see if there's any questions that have come up there. You guys are quiet. They say in education, like in education classes, that like if you wait long enough, someone will feel so awkward they'll come up with a question, which usually is a good thing. I'm not sure I believe that with you guys. I think you'll just stay silent. All right. Okay, so I'm just kind of thinking through, making sure I know where I want to head with the next 10 minutes. I think we're going to talk about size, ionization energy. Oh, I love this stuff so much more than everything else we've done this semester. I would do this any day over like conversion factors. Okay. All right, let's use this slide and let's take sulfur that we did before. And then let's also look at, no, I lied. I want to do boron, oxygen, and aluminum. Okay? So we're not going to go through the quantum numbers in detail, but I do want to talk about the electron configurations, and we'll probably look at orbital diagrams too. So maybe just take a minute for the sake of, practicing yourself a little bit, and go ahead and draw the orbital diagram for each of these. And then maybe we'll talk about shape from the side of look at the periodic table, or not shape, sorry, size. Look at the periodic table and determine size, but then we'll also use the orbital diagrams to kind of like visualize some of the ideas. Okay, so double check you have these correct. I'm also going to write down the electron configurations just as like a reminder. Okay, couple quick notes. Aluminum and boron, they're in the same column on the periodic table. So we know they're going to have the same number of valence electrons. That number of valence electrons corresponds to the column that they're in. So they're in the third column, skipping over the transition metals. So they're going to have 3 valence electrons. You can see that in their orbital diagram or in the electron configuration that the 3 are in the 2 in the S and 1 in the P. Okay, so remember, this is like the connections we have and why they are grouped into families and therefore have similar chemical properties, because they have that same kind of arrangement of their valence electrons, same number and same arrangement. Okay, so when we look at these, size, the best thing you want to think about with size, and that's very related to ionization energy, we'll talk about it in a second, but you want to think about the 3, now this involves Z effective, but it's like a little bit more detailed. You want to think about these 3 rules. I'm going to show you where they are, and then we'll just come back to them. So the valence shell, the number of protons, so those are the 2 things that are incorporated into Z effective, and then any electron repulsion. Okay, all questions about size, particularly when we're talking about ion size, can be decided using these 3 kind of in an order of priority. And then the other thing to remember is that the smaller something is, the higher its ionization energy is going to be. Okay, because small things means the electrons are close to the nucleus, which means they're low in potential energy. And the other way of saying low in potential energy is there's a strong attractive force to that nucleus. Okay, so big atoms down here, easy to remove those electrons, so they have a low ionization energy or low amount of energy to remove an electron. Elements over there, small, high ionization energies because the electrons are low in energy, potential energy hard to remove. Okay, so high ionization energy. Okay, so keep these 3 things in mind. We're going to take those back. Well, maybe I can stay here so we have them in front of us. So the elements we were looking at were oxygen, boron, and aluminum. Okay, so if we just look at their position on the periodic table, remember that they get smaller going across a row, So immediately I can look at boron and oxygen and say, oh, oxygen's smaller because it's further down the row. And then if I'm looking down columns, it gets bigger as I go down a column. So now between those three, I know aluminum's the biggest, then boron, and oxygen's the smallest. I don't know why, but your textbook loves to do like, order these in decreasing atomic radius, right? Instead of just saying like, which one's smaller? And like having two options. It like wants you to order them amongst 3 or 4 or 5 choices, whatever. Okay, so in more detail, the way we would know that is that boron and oxygen have a lower valence shell. So aluminum must be larger. Okay, between boron and oxygen has more protons, so the electrons are pulled in tighter. And then electron repulsion has nothing to do with it in this instance. Okay, what about if we talk about the ions? Okay, so I'm going to use a different color. What if we're saying the ions that these form when they participate in ionic bonding? Okay, when you're drawing an drawing an orbital diagram or writing an electron configuration, it's pretty straightforward. You either remove electrons that are high in energy, or if you're gaining electrons, you add them to the lowest energy orbital that's available. So for boron 3-, we're going to get rid of those 3 electrons. It's not a coincidence that you get rid of an entire shell. That is usually what happens, is you're going to remove an entire shell worth of electrons. So aluminum 3+, same thing. All of those would be gotten rid of. With the electron configurations, you're just going to remove those electrons. And with oxygen, you're going to add electrons. So it says we're adding 2. So there's 2 open spots within that subshell. Again, that's very normal for the shell to fill in completely. That's why they have these characteristic charges, because they're either eliminating a shell or they're filling in a shell. And then with the electron configuration, I would just put a 6 there now. Okay, also, remember, these are now isoelectronic with noble gases. So boron, since it lost electrons, it went down, and it matches up with helium now. Aluminum also went down, but it now matches up with neon. And oxygen finished off its shell, so now it looks like neon too. So O2- and Al3+ are all equivalent to neon in the sense of their electrons. Obviously, the protons are still different, but they have the same number of electrons. They have the same valence shell. And if we get this back to size, this can be an interesting comparison with size. You could have a question that said, which one's larger, O2- or Al3+? Okay, so we go through our 3 things. Valence shell. Well, they both are in the 2s and 2p, so that can't be helpful. Number of protons. Okay, well, aluminum's got 13 protons and oxygen has 8. So there's our answer, okay? Aluminum is going to be much smaller because those 13 protons are going to suck those 1s, 2s, and 2p electrons in much tighter than oxygen would. And then I guess one other thing, last thing I'll say, is that we often talk about the size between the neutral atom and its ion. So like oxygen versus oxygen 2-, that's always going to get larger due to electron repulsion. It's still at the same N level. It still has the same number of number of protons. It just gets bigger because of electron repulsion. When they're positive ions, you're losing an entire shell. So it gets smaller because you've lost an end level. Okay, you've completely eliminated one of those shells. So keep those 3 ideas in mind, and you probably will be able to predict the size every time. And then remember, size is connected with ionization energy. Smaller it is, harder it is to remove the electrons, higher ionization energy. Okay, send questions, email questions in the next couple days if you have them. Take a screenshot of where you're at, especially if it's math. A lot of the times, if you just take a picture of your work, like, I can identify pretty quickly what you're doing wrong. Okay? All right, happy studying. Hello.